People pay more to buy carbon fiber PLA to get stronger and stiffer parts, but I've already proven it's a scam. So this has become a series now, and we name it Cap or Fact. So after those videos, this company approached me, and they claim they solved every problem we found. And boy, oh boy, do they make claims. We're going to test every single one of them in this video. Their magic trick is something called coextrusions, where they actually take a piece of carbon fiber filament and wrap it in pure PLA. Just think of the toothpaste you had as a child with the colorful lines in it. So the idea behind that is that pure PLA loves to stick to pure PLA. Layer bonding will be very strong. Also, in addition, because of the PLA sleeve, your printer will be protected from wear and tear because the fibers never touch your gears or nozzle. So that's all nice, but here's the catch. That only works if the carbon fiber stays in the middle of the filament. But as your filament melts, everything starts to melt down, blend and mix in here. So will the carbon fiber actually stay in the middle of the filament? I have a guess, but we're going to need to prove that. To figure this out, we're going to look at 3 stages of the material: the filament itself, an extruded strand, and a printed part. And we cut cross-sections through the layer and see how the fiber distribution is. But here's the fun part. To get a clean cut through the part, we're actually going to freeze it in liquid nitrogen to avoid layer smearing while breaking. And then we're going to gold plate it using sputter plating with plasma, and then put it into a scanning electron microscope. Don't worry, I will explain how all of that works later. So yeah, we're going deep into material science this time, using more analytical tools than ever in one of my videos. Setting this up took hundreds of hours and millions worth of equipment. If you like videos like that go into real material testing and not just shits and giggles, consider subscribing. It really helps us out, letting YouTube know that there is an audience for videos like that. And it also lets me justify stealing more liquid nitrogen from my colleagues. Alright, welcome to the 3D printing lab. Time to print with this mystery material. First impression? It actually feels quite flexible, which is good because carbon fiber PLA tends to snap inside of your AMS system. We are going to keep this little specimen for our electron microscope. This will give us the results if the carbon fiber is even inside of the material, on the material itself. So let's put that printer into the, let's put that material into the printer.
Don't love your job, job your love.
So one good side effect of their co-extrusion is actually for your AMS system, when it grabs the material, the pure PLA shell should protect my intricate little gears here, so it does not wear down my AMS system all that much. So let's print our test specimens now. We will print again 5 specimens per axis per test we're doing. So these are the little plates for our SEM machine. So we take our sample and put it on there simply with a little double-sided tape. And then we put it into this little machine. So this machine is a gold sputter setup, a plasma sputterer. So this little target up here, what you see, is a pure gold disc. Yes, hundreds of dollars per gram gold. So what this machine actually does, in order to for our SEM to get a signal and read the surface of our sample, we're not looking on it optically, we're looking at it with an electron beam. We have to make our part conductive. And this machine adds a thin, nanometer thin gold layer onto our sample. And what happens when I close that lid is we're pulling a vacuum down to nearly the vacuum of space. And after that, there is a high current applied and a little bit of inert gas is added. And the gas atoms basically get excited and they bump into each other and they release energy that grabs gold particles from our gold plate and freeze them so they can fall onto our part and put a perfectly even conductive layer of gold of our part, just nanometers thin. So let's start this setup. So this beauty is a SEM, a scanning electron microscope. Normal microscopes use photons, so light, to visualize whatever you're looking on, and it is concentrated or enlarged by lenses made out of glass, most likely. This one uses an electron beam, so it emits a little electron beam and it's focused also by lenses, but these ones are magnetic lenses, so they're not there physically, it's just a magnet field where the electron beam is concentrated. This electron beam basically scans over the surface. So the electron beam basically interacts with the atoms of whatever you're looking at, and these ones release secondary atoms back, and they are detected by a detector. And so bit by bit, pixel by pixel, it reconstructs whatever you want to look at. In order to use the machine and the electron beam, we have to pull a vacuum that is close to what is on the edge of space. So the electrons can actually flow freely and don't get scattered by air. So let's fire this baby up and see if their claims hold true. Vacuum on, you want to pump. So our vacuum is complete. You already see it's a strange table and I don't touch it. It's actually weighted on the downside. This is an air table. So even microscopic little movements through me walking here or sitting on this chair can mess up my scan. What? Okay, so let's look into our images. So this actually is the undisturbed filament right off the spool. We broke it using liquid nitrogen and we zoomed in. And as you can see on this image, the carbon fiber in the filament itself is in the middle, and outside you have an undisturbed shell of pure PLA. That's something I was expecting because, yeah, like, why would they claim if it's not true that they did it? So this one is not a big surprise. What is a big surprise to me is actually this image. So this is an extruded strand of this coextrusion PLA. And as you can see, the carbon fiber actually stays in the middle of the extrusion. Something I didn't know, I didn't believe in, but it actually stays in the middle and you have an undisturbed layer of PLA still around it after it went through the nozzle. So that's really awesome. You can also kind of see in the background there, where it fades out, that the PLA itself is very smooth. So you don't have carbon fiber sticking out or disturbing the layer around it. Of course, it's a little wavy because it was extruded into the air. But if we look on it from the side, you actually have a very smooth surface of undisturbed PLA. And this is why I think the prints look so pretty and nice, even though you don't have carbon fiber out of it. The other stuff, just ignore it. That's my skin cells because I touched it without the glove. So here we have a printed part using this filament. So as you can see, the break line is very clean. Because of the liquid nitrogen, we have one basic cut plane through everything, which is perfect for us to focus our microscope on. So if we zoom in a little, you can already see there is carbon fiber still in the middle of the strand, and these like nothing is inside of the layer boundary itself. So I actually measured it out, and the distance between the different carbon fibers is around 30 to 40 microns. But the distance from the carbon fiber to the actual melt zone between the layers is also about 40 microns. That means that in the layer area, the distance between one carbon fiber and the other is about double that, so about 100 microns. So that means it's not just pure coincidence or dumb luck that we focused on an area where you have no carbon fiber in between, because I looked through a lot of areas of this whole thing. And as you can see here and there and there and there is nowhere carbon fiber in between layer lines. Of course, you have this one laying down there, but this is just after breaking. I basically bent it a little bit. But one very interesting thing I saw here, even better than in my carbon fiber PLA videos, is if we zoom a little bit in on especially this one, then if we get closer and closer, first of all, we can see that up here, the carbon fiber actually detached from the polymer while breaking, and you can still see the kind of like surface pattern on the polymer, and you can still see that it matches the other one perfect, but I want to concentrate on this carbon fiber. So if we zoom in a little more, you can actually now really well see the gaps, the retraction of the polymer from the carbon fiber itself. That means also this manufacturer didn't solve the issue that the carbon fiber has attaching itself to the polymer of PLA. So the wetting problem is still not solved and the fiber was not properly conditioned. So if I measure it, so that's why in our last CT images you can only kind of see the gaps around the fibers because the resolution was not high enough. The gaps are between 800 nanometers and 1 micrometers, and the fiber itself only has 8 micrometers. So that's why the resolution is pretty much not there in the micro CT. Here you can see more images of the carbon fiber retracting from the filament, and you can actually see it all over the place in the whole thing. So I think the next thing to do is to see if it's also all of that is true in an undisturbed layer after CT imaging. Oh, right. So I think it's time to keep the lights on. Let me tell you about our today's sponsor. PCBWay is a long-time sponsor of our channel, and PCBWay provides you everything from PCB design, manufacturing, but also 3D printing. You can get metal 3D print, plastic 3D prints in every kind of polymer, and they don't bullshit you with carbon fiber CF. So try out PCBWay and help out the channel. So let's get on to CT. The one thing that immediately jumped my eye when I opened up the CT images is like kind of the starry nights that I was presented with. Here is a picture of it. We have those really bright little specks everywhere, and like here is even one in a star form. So they're super bright, and you have to understand in CT imaging, brightness means density, and something like this where you actually can see those kind of light rays emitting from it, that means metal content. So I was really surprised to find metal inside of a PLA-CF coextrusion filament. So I looked a little bit deeper into it, and that is actually called carbon black. This is because the carbon black is made in a furnace, and while doing that you get impurities, and that can be nickel or even like metal, like Fe, inside of the compound. Carbon black is actually used to make filament black. So that means this is a little bit more abrasive. So even though they put the carbon fiber in the middle of the strand to protect your nozzle from wear and tear, those carbon black particles, they are sometimes on the edge of the extrusion, so they will touch your nozzle. And they are hard and they are abrasive. It's basically like printing sandpaper. By the way, I want to explain one thing, because in my last video you actually mentioned it, that we have those huge gaps here, and like somebody actually said, it's a skill issue of mine, I don't know how to print. What you see there is the natural gap in between layers. So not the layers on top of each other, but extrusion lines to the side of each other. Because you basically print a layer and a layer and then a layer and a layer, what you get here is kind of a rhombus of density missing. So that is what you see here, because the thing was slightly crooked. These are the layer lines in that direction, and these are the layer lines in that direction, but they stop here because we look at it for an angle. So that is actually why, and now we're diving into another topic, we are looking into bricklayer printing that much, because bricklayer printing solves exactly that. If you have your layers angled to each other, what you get here is, instead of a rhombus like here, you get kind of a triangle with way less density lost. So that just as a side note. But let's continue on our CT imaging. So this now is a close-up of the carbon fibers inside of the material. First of all, one thing we can already confirm, what we already saw in our microscopy images, the carbon fiber actually stays within the extrusion. You don't have carbon fibers on the sides of your extrusion. I found something else very interesting. In my last video I talked about those air bubbles that are present in this material. So of course I looked for them again, and I found them everywhere. But this time I looked a little bit closer and I looked into where they are located, if I can see any kind of pattern going on here. And what I found this time is that every bubble has a carbon fiber basically attached to it. And it's always reaching into the bubble itself. So you can see here you have the bubble, And here you have the carbon fiber sticking into it. And every little bubble I found in this specific filament had a carbon fiber directly attached to it. And here comes the burner. It's always in extrusion. So our cavities are always at the end of a carbon fiber. One of my theories is that the carbon fiber actually gets laid down, and because the material always hardens already back here when it's still extruding, the material around it is still kind of moving because it's squished by the nozzle extruding, but the carbon fiber itself is already stuck. The end of carbon fibers are basically sharp corners. What it does is the material detaches from here because of that corner, because of the stress concentration, and it drags out a drop where there is simple negative pressure or air pulled in. An air bubble is created. So I'm very keen into looking closer into that. I couldn't find anything online why something like that happens. So maybe we stumbled upon something new and you guys already wanted me to look into it closer. So I think that's a topic for our next video. Other than that, what can I say about the micro CT imaging? Their claim is true that the carbon fiber stays inside. The bonding is very good. And as you can see, the edges between the layers, here and here, if you compare them to our last CT images of carbon fiber reinforced PLA, they are actually way cleaner. So the whole print looks on a microscopic level way cleaner. And I think that kind of makes sense because if we look at the microscopy images of PLA-CF, you see that the outside of the filament itself or the extrusion strand is a wild mess. But here, if we look on the extruded strands that we did separately and photographed under great magnification in our microscopy, the surface of it is very smooth and clean. So I think the carbon fiber not only disrupts layer bonds, but it also does this cavity effect on the outside of the extrusion. And that is why in the last micro CT image we saw of PLA-CF, the edges touching each other were super edgy and like not consistent at all, which also weakens the material further. That's nice, but does it actually change the mechanical behavior of the material well enough that it's worth something? Because otherwise, all of this fancy thing would be as useful as the share button on Pornhub. Well, after imaging now, we are back on our standard testing machine. I brought our samples, and this time, as I already mentioned, we will do a standard 3-point bending test on those. Because in my last video in the comment section, you rightfully so pointed out that the biggest advantage of carbon-filled material is not its tensile strength, but its stiffness and its hardness when it comes to breaking. So we are going to test that and quantify that. I have our PLA coextrusion again in all layer direction, but I also brought carbon fiber reinforced PLA and classical PLA with me. I also, of course, have our tensile specimens ready. So let's set up our 3-point bending test. We place our specimen here. And let's move the machine down, medium down, we don't want to crash, medium down, 1.
They slid in my inbox like, hey good sir, we saw your video and yeah that hurt, but hear us out, we fixed the mess, new tech, new methods, stronger than the rest. They said coextrusion, my eyebrow rose, 2 materials, 1 nozzle flows, core is tough, the shell is strong. I said sounds cool but I smell a con, so I cleared my desk, I fired my rig, pulled out tools that go way too big, micro CT, SEM tensile machine. If you lie to me it'll show up clean. Is it cap or is it fact? Is this just hype in a data pad? Last time CF was just cosplay, now let's see if this one earns its pay. Is it cap or is it fact? I don't trust words, I trust impact. I test the stuff, I break the thing. Welcome back to Cap or Fact, baby, let's begin. Baby, let's begin.
Oh wow, so where co-extrusion actually has more force but less displacement. So carbon fiber after all does something for the part. So we finished our mechanical testing, and before we come to the conclusion of this, I actually want to point out one comment on our last video where a guy that has a lot of knowledge apparently about these blends of carbon fiber with polymers actually pointed out what I already suspected and proven. It's the wetting of the fiber, or he said it's called sizing. I myself, I'm from injection molding as well, so I know that issue that some polymers can't stick to the filament. And what we saw in the microscopy image is exactly that problem, that the fiber doesn't bond to the polymer itself. But let's move on to the mechanical testing. So I would like to reveal the first thing of their claims, that was stronger, stiffer parts. So let's concentrate on the stiff a little bit. We did our 3-point bending test again and compared to normal PLA and PLACF from our last video. And yes, it actually works. The parts are way stiffer. It's about 15 to 20% difference to the carbon fiber PLA and the pure bland PLA. So it actually did something. I'm just not sure if it's actually that the coextrusion itself and the layer bonding does something positive, or if it's just because what they also claim, use longer carbon fibers. So the longer the fiber is, the more energy it can take, even though it can move around in the polymer itself. So we might have to look into that a little bit more, but I would say that's a fact. So the second claim was that they have stronger layer bonding, and we tested that using tensile strength testing, especially the Z one is the interesting. And as you can see here, yes, it actually holds better, but that was kind of predictable because the layer bond is not disrupted by the carbon fiber anymore. I think for me the biggest surprise was actually that the carbon fiber stayed in the middle of the extrusion and didn't touch the layer boundaries. So that is what gives this material an advantage over carbon fiber reinforced PLA. The thing is, the other claim with non-abrasiveness. There I'm kind of undecided because yes, the carbon fiber is not on the outside of the extrusion strand anymore. It stays very well inside the extrusion itself, but you have this carbon black that is also very abrasive. So on the abrasiveness, I would give it a cap, I think. So overall, the rating of this filament is fact. They actually solved most of the issues we had with carbon fiber. Maybe if they add another blackening agent instead of carbon black, that would help a lot. But other than that, I think it's a viable option for carbon fiber reinforced printing. But there is still one issue left, right? The health impact of carbon fiber. So we had loads and loads of comments on our last video about the health impact on carbon fiber. And I'm actually planning to do a video on that. You just have to wait a little bit because I want to do my job well and bring you like reliable data. Other than that, I hoped this episode of Cap or Fact was to enjoy, and see you in the next video.